highway really saw the benefit of 2D modeling. And so in 2019, they came out with a new reference document. And through the years, I mean, we've been looking at different ways of modeling hydraulic river systems, but just the technology just wasn't there to be able to model it in 2D as it is right now. And so probably right around the 2000s is when 2D modeling started to become more of a buzzword. But now it's a lot more user-friendly than it was back in the 2000s, or even when it was still just 1D modeling back in the 1960s, where you had to use cards and whatnot. And so it's just a lot more precise and less assumptions that you have to predict, going from a 1D model to a 2D model. So it was recommended that 2D modeling be used for bridge projects. And then in 2019, the DOT, when they updated their hydraulic manual, they recommended to include 1D or 2D for fish passage and bridge projects. But under their hydraulic analysis in Chapter 7 for fish passage, they actually require it. And so if you want to work on fish passage projects for the DOT, you're probably going to have to get some training with 2D modeling. And there's an NHI course, which I highly recommend. It's a 4-day course to be able to go through to learn a little bit more. So this is why it's so important right now than it was 5 years ago. Just the push, and it's just a better way of looking at river systems. So let's take a look at an example project. This bridge project that we're going to look at, we're going to derive some water surface elevations and scour depths using the program. We're also going to check vertical clearance and channel migration zone criteria. So these are just a couple of things that we're going to look at. There's other components that you typically look at when you're doing a bridge project, but I'm just going to focus on these criteria. This project crosses the Tusi River, and it flows south to the Walla Walla River. So just kind of some dynamics of the basin area. The existing bridge was built in 1914, and it's 115 feet in length. And the other thing that we know, it was identified to be structurally deficient, and in the bridge inspection report, it was determined that the bridge had a scour critical code of 3. So now this is kind of giving us a background of what the project is all about. And the biggie is the scour critical code 3. What does it mean? It means that the scour limit is at the footing, and it's unstable. Either assessed, being that you can physically see the bottom of the footing, or it's been calculated that it's going to be below. So knowing that, something should be done about it, right? Some type of plan of action. So now let's start looking at some bridges or some pictures of the site. And so we were able to find some archive photos, and this picture here is actually from 1909, before the existing bridge. And so we can see that there's a pony truss structure here, and it spans the main channel. And then we have several bents on either side of the main channel, and then we have a school there. So this just kind of gives us an idea of what was there before the existing structure. And then we can see where the flow of the main channel, and then we can also see on the right here some side flow that's coming in. So that kind of gives us an idea of what it was before. Now looking at the existing structure, the 1914 bridge structure, we have a Luton arch now. And it's not as long as the 1909 bridge. The other thing that we see is that the main channel is now, it's meandered on to the where the offside channel was, and this is actually hitting the road approach here. And so this is a drone shot that was taken of the bridge. And so we're looking at just the components now of the river, of what it looks like now compared to back in 1909, which was great when you can find historical photos of your project site. The photo to the right here, we're looking upstream, and you can see where the existing school building is, and some buildup of riprap, the bank, and then we got the center pier there. So looking at it, we're just kind of gauging what the site has, and so we're looking at our site conditions. And so what we're trying to do is we're trying to set up, okay, what are we going to need for our modeling? And so one of the things that we need to look at is, okay, site conditions, right? How big of the basin area are we looking at here? For this particular project, this basin area is approximately 497 square miles. And then we're looking at, does it have any gauges nearby? Does it have a gauge at the bridge site? How far upstream, downstream is a gauge? The other thing that we look at is finding information about FEMA. Do we have the flood insurance rate maps? What is how far, what year has it been, do we have an updated year that the flood maps have been defined? And so here in this aerial shot, we were able to overlay the FEMA map boundaries for the 100-year to see how wide the floodplain is. And you can see where the little school is at. So it has a very wide floodplain for this river system. So again, we're gathering information for our project site. So when we're doing our modeling, we can take into account all these considerations. Moving along, now we're looking at our hydrology. So we kind of talked about FEMA, but now I'm looking at the FEMA flood insurance studies. And so was there a study done on this river system? And luckily there was a study done, and we were able to, in 2002, and so we were able to get flows upstream from the proposed site that we were looking at a location called Boyle. And so from the FEMA flood study, we were able to get the higher flows at this location. The other thing that we looked at was what kind of gauges did we have? And so at that same location at Boyle, the USGS had a gauge that is no longer in use, but it was in use from 1925 to 1989. So that was 64 years of record of flows that you could use to generate mean recurrence interval flows. And so when we did that, we found that those flows were less than what the FEMA 2002 flows were at that same location. So that's why we stuck with the FEMA flows and not the USGS flows. On top of this, we were very fortunate that the DOE had a monitoring station at the same location. My guess is that they just took over the old USGS gauge in 2007 to the present, and was able to capture an event in February 7th, 2020, which was fantastic because now we actually had an event that we could use to validate the model. So going through our hydrology, we're able to then figure out, okay, what would be our design flow at our stream? Because then these would be the flows that we would use to input into the model. So that's our hydrology, going through all these different forms of information and then putting them together like our puzzle pieces to be able to get the design flows that we're going to need for the model. Here's that February 7th flow that I was talking about. that was able to be captured. So we were able to capture the flow upstream, and then we were also fortunate that the county was able to go out and take photos during the event. They actually missed the peak, and so this was where the flow was during when they got there. But looking at the pictures, we were able to see where the high water line elevation was, so we could capture that piece of information, so we could use that to validate the model on that. So that's wrapping up our flows, and now let's go back to our site condition. Now here we're looking at stream stability. So we're back on our site visit, and we're looking at geomorphic assessment. So we're doing a lot of gathering information still. So I haven't even gotten into the modeling portion of it at all. It's just gathering all the information that is necessary before we can actually go in. And so here we are looking at the geomorphic assessments of our bridge. The top photo shows I'm on the south bank looking north upstream. And so we can see the exposure of the center pier. And we can also see the gravel bar buildup inside the Luton Arch. We can also, as well as looking upstream, the eroding bank. And so some of the things that we want to capture when we're out on the site visit is the channel sediment, the size of it, doing a pebble count, locations of the gravel bars, just kind of getting a feel of the size and the movement of the sediment, seeing if it's a flashy system, where the bank erosion is happening. Is it just localized pier scour that we're looking at? Do we have contraction scour going as well? Looking at high water line, telltale marks, or just anything that we can capture while we're out on the site visit. Seeing if we could actually visually see where the floodplain dimension, if we can visually see the floodplain width while we're on the site. If it's really wide, that's kind of a lot harder than if it's a smaller system, but it's something to keep in the back of your head. The other thing is the amount of debris, large woody debris in the system, how much is in the river system as well. And for this particular project that we were looking at, what the surrounding area is. Is it urban? Here it was all farmland. Are you mountainous? Where are you in your watershed system? So we're looking at the stream stability now of the system. More site visits of photos. Again, we're looking at on the upstream side of the bridge. Again, you can see the exposure of the pier. We see more rock here on the south end, the gravel bar inside the Luton Arch on the north end. The center picture here, we're looking at the north abutment, which is pretty exposed as well at this location, compared to the south abutment, where we actually have rock outcrop at the site. So that's why the south abutment has not eroded away, because of the existing rock outcrop of the existing site. More pictures of the site here. Again, we're looking upstream, and we can see the riprap around the toe of the roadway embankment here. Center picture, we're looking at the bank erosion that's going on, and then it stopped here, and I was wondering why it stopped. Well, we had some down trees, but we also have riprap. The riprap along the roadway stopped at this location, so it's creating some stability. So that's why the bank hasn't continued to erode further from this point. Looking across the channel is the overflow area, and you can see the bank lines where the existing tree lines are at, the gravel bar, again, trying to get a sense of the shrubs and trees and the roughness of the area as well. So that was our the geomorphic. Now we're looking at land use changes. For our basin area, where we're definitely in a rural setting, and we're not going to see a lot of huge changes as we could see in an urban area. But so for this basin, you can definitely, this is on Google Earth. It's all Palouse farmland down, probably over half of it, and then you have a mountainous on the headwaters of it, but not very much change, unless there was farming practices or something, you know, that we were told or seen for this land use change. The third thing is to see the overall stability of the stream system. This chart is great because we go through and we look at channel patterns. Is it a meandering? Is it straight? Is it braided? Well, it's very meandering for our system. So we highlight that area, right? And so it brings down where they're in a 3, 3B, or a 4 category here. We look at channel type regarding the sediment loading. Do we have mostly suspended, a little bit of a mix, or just more of a bed load? And so based on our meander, I was guessing that it was more of a mixed load. Looking at our meanders, are we shifting? You know, where are we? Are we high, low, braided? Definitely not braided yet, but shifting and cutting shoots and so forth. So definitely in the area 4 of our of this type of stream assessment. So it's looking at it's relatively stable, but not super stable. So it's kind of like, you know, not bad, but not good either. So it's kind of somewhere in the middle. So this kind of gives us a stability of where this river system is at. The fourth, we have to look at the lateral stability of this system. So how is it laterally moving back and forth? Well, first we need to look at what the minimum, what we call a minimum hydraulic opening is, or what the bank width should be, and using a 2-year flood event can help establish what those what that width would be. And now I ran the model in order to figure out what this width was. And so this width is telling me I should have a minimum opening of approximately 240 to 290 feet. As you can tell, the existing structure here is only 150 feet. So we know that the existing structure is definitely creating a constriction point on the river system. And so a good way of thinking about this is like, you know, when you have a worm, if you hold the head of a worm still, the body wiggles back and forth. That's exactly what a river is doing. The bridge is the constriction point, and the river upstream is just wiggling back and forth, meandering back and forth, and trying to find some stability. And so we know that the existing, that's one thing that looking at the stream stability evaluation is that the existing structure definitely needs to be a lot wider based on this quick analysis that we're looking at. So that's one step laterally. The second thing that we need to look at is the channel migration zone. And so the channel is, when it has a wide floodplain, it's going to meander back and forth inside of this floodplain. And so trying to establish where those limits are, on this site, we were able to use older photographs to be able to capture where those limits were, to establish a northern limit and then the southern limit. closer to the bridge, we were seeing that the channel migration zone was about 345 feet in length. The further upstream you go, some of these were over 500 feet in length. And so when we're looking at proposing a new bridge crossing, you would probably want to be able to span the whole channel migration zone. It can get very expensive doing that. And so as long as you can span that minimum hydraulic opening and know that you're still within that migration zone, then you start looking at other components. But these are just some key points that you, as a hydraulic engineer, you would have to bring up to the team as critical points. So the fifth component that we look at is the vertical stability. And so, and this is where in bridge inspection reports, these sounding files are tremendous because they tell quite the story. The teal line is the existing ground line from 1914. So we can see how high the ground line was compared to the bottom of the footing here, and where the thalweg was. So our thalweg was between on the south end of the Luton Arch. And then in 1992, we have the red line. So the ground line actually went up in 1992, and it moved the thalweg closer to the south abutment. So everything started to shift. In 96, another event came through, and it lowered everything. And so now we have the ground line elevation way lower than where the existing was. The green line is from 2012. So again, we see more aggradation coming in. So we see more sediment. It's still lower than what the existing ground line was. And then in the last sounding that we see here is in 2026, which is the orange line. So the thalweg is actually shifting back toward the north abutment here. So it's not in the south span anymore. Now it's shifted back to the north. And so I really love seeing sounding files because it not only gives us a vertical, how much soil vertically has been eroded or degradation has happened, but laterally how much has been shifting between through the years. And so it just tells you a great story of what's going on. So now that we've gone through and did our site assessments and everything, now we can actually start hopping into the model. And so the very first thing that we need to do is work with our survey crew and get our survey points. And when using the model, you can import LiDAR, you can import raster files, you can import actual stream gauge, or not stream, or stream bathymetry files. And so this is a combination of LiDAR and actual stream crossings that was used. So the tighter survey points are around the stream versus out in the floodplain area. These are our LiDAR points. Using the scatter data, you can then generate a contour map, which is then color-coded based on elevation. And I like looking at it from a 2D view and then flipping it to a 3D view, because when you look at it from a 3D view, then you can actually see where there's any errors or holes in the contour or in the survey. Any bad points will just come out. And so one thing that I've learned is that using this model, you definitely need to brush up on your surveying skills to be able to understand all of that lingo again, to be able to have a good map, a good scatter data map to generate the next step. So once you're happy and the survey crew, you concur with your survey crew that this does look correct, then you can go on to the next stage, the next step, which is the mesh data. So now when we develop we're taking that survey and we're dividing up the area of interest in components. And so the area outside of the river, or the furthest away that we're looking at, this mesh area, the farmland area here, doesn't need to be as tight for components, for data, as it is in the river system. So my river system, the way I've defined it to be a lot more tighter. So then so that's why it's a lot darker in those components. So again, I'm looking at it from a 2D or a plan view versus the 3D view, and you can see the tightness of the mesh here is a lot darker than it is out in the extremitories. The tighter you make your mesh, the longer it's going to take to do its computation. And the more points you have, again, the longer the computation, but the more accurate your results will be. And again, if you have any points that are at 0 or are off, you're going to see them once you flip it on a 3D view. So that's the second. This is our first layer, our mesh layer. The boundary layer is where we define our flows. Now we start inputting our flow information. So we have our inlet. We define where our flow will be coming in, and we can only define one flow at a time, unfortunately. Like in the 1D models, you can input all your different flows. In the table here, you can only do it one flow at a time. And then on the downstream side, our boundary condition, we establish it as an exit subcritical flow and define it using normal depth. And it uses the mesh contour elevation, or it uses the mesh that we have defined, and then we can come in and give it a Manning's roughness and what the slope is of the channel, and it will generate, and then we input the flow here as well, and it will generate a water surface elevation for us, the downstream water surface elevation as a starting point for the model. So this is the boundary layer condition. So we had the survey, we started with the survey, we had the mesh, and now we have the boundary layer component. Moving along, the next parameter that we look at, in the model, they define it as material. And so the materials is basically the roughness of the land area. So these areas we're looking at how we defined our mesh, and so our materials match the mesh areas as well. And so I've identified the channel as blue. So everything in blue has a Manning's roughness of 0.03. And then we have top of bank, which is like an aqua teal, an overbank area, which is where the tree area is at. And then I have all the agricultural in yellow. Our roadway is defined in black. And then I have an pretty big open ditch that I've also defined. So all these areas have a roughness element tied to that. And again, once you come through and define all these areas, then we're able to then move on to the next layer component, which is the monitoring layer. So we want to be able to define locations in the model where we want to double check water surface elevation, velocities. And so I chose on the downstream side of the existing bridge, right on the upstream side of the existing bridge, upstream of my survey, and then some right before the bend. So these are 4 locations that that I have selected to monitor for the model. So these are the layers that we work on in the model in order to then run the simulation. So once we have those 4 components, we have the boundary conditions, we have our monitoring location, the materials, and the mesh. We can then create this simulation file and run it. As I mentioned earlier, the more data points, the tighter the mesh, the longer it's going to take to simulate your model. It can be anywhere from a minute or 20 minutes, depending on how much information you have going on. And then you can define the number of time steps that you want it to go through and generate flows as well. Here we only did 4 hours that we looked at. Once it goes through its computation, and then it spits out up above the results. So we're looking at water surface elevations, water depth, velocity, magnitude, crude number, and stress are the outputs that it generates. And so this is looking at the extent of a water surface elevation based on color-coded using elevation. So everything in the red is around 940, yellow is around 937, and then green is around 934 in elevation. And so the other way you can look at is running your mouse in the area, and then it pinpoints, it gives you actual elevations that you can look at. You can also change the range of the elevations. You can make a contour at every half a foot or every tenth. Becomes a lot, so it's up to you. 1 foot to me is practical, or 2 feet, depending on how large your the area that you're looking at. But this gives us this event is looking at the February 7th 2020 event that occurred. So we were trying to see if the model was able to show the extent of what the actual flood was during that time. This is the same event, but now we're looking at the velocity, the magnitude, and so here I highlighted the highest velocity, which is around that inside bend, which was around 14.7 feet per second in velocity. The other thing that you can see is it has velocity vectors, so which is what is so powerful in this 2D modeling, is that you see the flow direction of the flow and the path that it's taking, how it's coming into the bank from the floodplain, and then going back into the channel, and then back into the floodplain, and then back around. It's hard. You can't capture that in a 1D model, and so in a 2D model, you can definitely capture it using these flow vectors to help figure out these flow paths. Looking at it from a 3D result, again, you can see those velocity vectors in here as it's flowing in the floodplain out here versus in the channel. And then if I zoom into the bridge area, then I could see what, how it's looking around, working, or how it's flowing through the opening. This event did not overtop the existing roadway, but it definitely reached its banks. And again, you can see the velocity flows based on the color range. Here, it was every 2 feet per second. that we had defined it. Another cool component is you can do some animation and actually see the flow path of the river system, where and then we can come back and reverse it. Just another tool to be able to come in and see how the flow is flowing versus just looking at it from those velocity vectors. This is a short little clip of just 16 seconds or less than that, but you can go in and change that animation. The other thing that you can that SRH-2D can generate is profiles. You can tell it exactly where you want, or you cut your cross section for water surface elevation, or you can also generate water surface elevation profiles. And so for here, we're looking at the cross section water surface elevation at the existing bridge, and then I was trying to capture what the elevation was during that storm event to see if it matched the high water, what the tolerance difference was between the two. So I was trying to validate the model based on that location. I also wanted to see how much of a backwater the existing bridge was is creating. And here we were able to see that it had almost a 3-foot backwater, 2.6 feet of backwater. And so these are very important pieces of information to bring to the team when looking at hydraulics. The last thing that that I wanted to talk about is the vertical clearance issue. It's a criteria where it's recommended to have at least 3 feet of clearance from the 100-year water surface elevation to the low chord. Looking at the existing structure, I had the first archway, we have a foot, which is we're under the 3 feet here, and then the second arch, we're almost at 3 feet at the center, but not the 3 feet is not attained at all. And you can also see how the water surface elevation kind of drops down as it comes through, so it's a little bit higher for the 100-year, and then so when looking at this is huge in the difference between the 1D and the 2D, because a 1D could capture just the higher elevation and extrapolate it all the way across, or it could capture something average in between, and it would be a constant elevation versus what the elevation that the 2D model is actually showing us. So again, just something to take into account. And in some systems, 3 feet might not be enough. You might need 6 feet of clearance because of the amount of debris that's coming down the system. Or if it doesn't have very much debris, then you could be under 3 feet and do some engineering justifications on that as well. So the last thing that I was going to discuss was bridge scour. So that's another feature that that the model can generate output information. So it's a bridge called bridge scour, and it's under the map component features. And so the very first thing that you need to do is define your attributes, your bridge scour attributes. And so basically there's 6 components, and you're looking at the contraction section. So that's the bridge that you're defining. What is that section, that contraction section that you're looking at? The second component or attribute is the approach. Here is the red line here. So this is the flow approach, right? The width that is that you're looking at. Then you got your center line of your river system. You have your bank at the bridge location, and then the toe of the abutment. And then if the bridge has any existing piers that you want to be able to define. So once you've defined these attributes, then you go to the next step and you start inputting information about your soil, the sediment, the size, and so your pebble count that you got when you were out on your site visit or from the geotech report. The mesh that you used, the water surface elevation that it generated, the water depth, the velocity files, and then what type of contraction scour approach you want to look at, and the abutment scour conditions that you're wanting to look at, the name of the file, where you want to place the name of this output file, and then do a quick view of what the file is, and then export it. Export this file to the hydraulic toolbox. So now we're looking at the hydraulic toolbox, which is a different software program that is from the Federal Highway that I would say the majority of a lot of hydraulic engineers are using these days. And Bridge Scour is just one component. And so if you input the file in here, and you just want to make sure that you double check the information that is being inputted, because sometimes things get lost. And so you just want to redefine everything, that everything is correct for your long-term degradation, your contraction scour, your pier scour, and your abutment scour components. You then run the computation, and it generates a summary table for you, what the scour depths are, and then it could also generate a plot preview of what those scour depths are. Or again, this is a side software program, not in the SRH-2D model, but it kind of goes hand in hand with it. So it generates a file that you can input into this other program. And so that, in a nutshell, is my presentation. Again, it's a lot of gathering of information to be able to run the model, but working with the team and to be able to provide those hydraulic conditions to your team, working with the geotechs, working with the bridge designers, working with the civil roadway, the surveyors, the environmental folks. It's a lot of fun. I enjoy it a lot, and I'm happy that I was able to provide this presentation to you today. And if you have any questions, I'd be happy to answer them.
We as well, Rose. Thank you very much for the presentation. We have a couple of text questions, but let's start first with anybody that would like to ask, over your mic. If you can unmute yourself, and if you want to share your video as well, go right ahead.
This is Ray Walton with West Consultants. I sent in 3 questions. Should I just go through them now, or?
Sure.
Okay. Again, I'm Ray Walton with West Consultants. We've run SRH-2D quite a bit, but my questions allude more to any two-dimensional modeling. Can you comment about the location of your downstream boundary? It seemed to me that it was too close to the bridge.
Yes, it was way too close, and it was when we were first looking at the site, we were thinking we'd just run a 1D model, not a 2D model. And after running the 2D model, we noticed that the downstream boundary should have been a lot further downstream. And so, yes, that is correct, that the downstream boundary condition should have been a little bit further downstream.
Right. I mean, the rule of thumb I tend to use for bridge modeling is at least 3 widths downstream.
Yes.
The second question is, did you calibrate the model, or did I miss that discussion?
I didn't calibrate. I just validated it using the February 7th event.
Okay, because the question that I had about that was, you talked about the high water mark on the upstream face of the bridge.
Yes.
That, of course, would represent the energy grade line, not the water. I mean, it would be the water surface because the velocity is 0. Was your model sensitive enough to be able to differentiate between the water surface elevation, the upstream, and the water surface elevation along the side of the pier, which would be lower by about the velocity head?
Yeah, I don't know, Walt. I mean, Ray, I wouldn't be able. I can't think of.
My point is that calibration around bridge piers is a little bit tricky if the model is not sensitive to pick up the difference between the water surface elevation at the upstream face and the water surface elevation along the side.
Got it. Okay.
Because they differ by the velocity head. So that could be like a foot or so difference. So if it's calibrated to a model that doesn't have that, the model can over predict the water surface elevation. The other question was the selection of your friction values. Can you talk about how you picked friction values in a 2D model, because they can be different from similar values in a 1D model?
I basically went off of what the FEMA flood study had generate what they had used, and then I also looked at just normal Manning's numbers for the for classifying agricultural farmland areas, and so I kind of used a little bit of what I could find.
So the FEMA model was a 1D model?
Yes.
Okay, all right. Okay, thanks.
Excellent. Thank you, Ray. We have a question from Barbara. Yes, sure. Go ahead, Barbara.
Hi, I'm Barbara Banjafon. I'm just a civil engineer. I was hoping that you'd get your model validated and then you would pop in new bridge sections, because it sounded like you're saying that the bridge span needed to be longer or something like that. I was like, oh, and then what happens? Like, did you run like 3 different models and did it extend further, I guess, north or north? Were you able to use it, or will you in the future?
Yeah. And so I couldn't, I can't state that information right now because the project is still ongoing. So I could only define what the existing conditions are. Yeah.
Well, but if you do get to do that, are you looking then at reducing the velocity and reducing the scouring velocity and the scouring, and that's the goal of it? And then is there any idea about like re-channelizing it, or we don't know yet because there's like property and right away and who knows? Correct.
Yeah, but definitely getting rid of the backwater, increasing the span to take into account the full migration zone, or at least the minimum hydraulic opening, and yeah, reducing those velocities.
Okay, cool. It was just fascinating. I really got what you were saying about the difference between the 1D and the 2D with that hydraulic grade line at the section. Like, thanks for explaining that in a way that I got it. I'm like, oh, that makes sense. Otherwise, I had no idea.
Yeah.
So cool. Yeah, and the backwater part, I'm like, man, it looked like it was in a different location by, I don't know, 50 or 100 feet in the model. I don't know. Anyway, thanks for your presentation.
You're welcome.
Thank you very much, Barbara. Anybody else have any questions for Rose? Remember to unmute yourself before asking. Okay, we still have 5 minutes. So, Rose, I would like to ask you one question. On slide 18, you mentioned you had different you had a graph of different ground lines, at different points in time. I don't know if you can share your screen again. and go to slide 18.
Okay, let's see here.
I'm more knowledgeable in chemistry, so I'm not very familiar, so the question might appear naive, but I was curious about the data on that slide. You know, I think the first data point that you had was from 1914. The first.
Yeah. Can you see this? The teal?
Yep.
Yeah.
Exactly. Yeah.
The sound. Yeah.
So first of all, I was curious, where do you find that data? I mean, historically.
This data is usually in the bridge inspection report. And so you would have to work with the county or with the local agency or with the state to be able to pull up their bridge inspection reports.
I see.
And so the majority of our bridge systems have a sounding file on them. And so it's valuable information.
How far back do those records usually go?
Well, they should start from, they usually capture the as-built from when the bridge was built.
Mm-hmm.
And then I know the DOT started doing bridge soundings probably around the 1990s. That's when their bridge scour program really started to kind of beef up. So I would say from the 1990s and on. So that's why you see 1992 as the second date here.
Yeah.
Because that's when DOT really started doing more bridge scour bridge information, bridge inspection on scour. There was more of a push. There was more of a push from the feds during that time period.
I see. One more question that I have that I was trying to synthesize, you know, combine my background with the things that you were saying, which in no way am I knowledgeable about. But I was thinking that you know what, how does the modeling community account for, or how can they account for future changes in weather patterns or patterns that have already been observed, and I assume they might as well affect even like stream flows, right? Turn like a more compressed high flow river into a more flashy one.
Yeah, I'm just starting to get more into the 2D modeling. Ray is definitely an expert when it comes when it comes to 2D modeling. I've spoken with him before on it, but that's a great question on how to be able to take those into account. The changes. I know hydrology wise for flows, you could increase your flows to take into account, you know, flows that are higher, but to be able to do those flash flood, you know, to be able to capture those more intense type, you know, events like you were talking about. I'm not quite versed on that information right now.
I was thinking from two different aspects. First of all, maybe higher flow, but also if there is a bigger span between rain events, let's say between flow events, what type of effect that can have on the riverbed in between, and if that how can it affect scouring or sedimentation if the topsoil, let's say, is more loose than it was if the flow is more constant throughout the year.
So I think what you're trying to say is like a steady flow versus an unsteady flow. So a steady flow analysis is looking at a constant flow versus an unsteady where you actually have a variation in flow. So you start at 0 and you go to like 100 and then it drops back down to 50 and then back up to 200. And so, so you're looking at how that sediment movement is being impacted with those different unsteady flow.
Exactly.
Yeah. And again, I'm still at steady right now, And so I'm still learning as we're going along. After all these years in hydraulic engineering, I'm still also learning as I'm coming along and trying to learn with others.
Well, thank you.
This is Jeff Rice. I'm a recently retired engineer, moved down here from British Columbia. And I thank you for your presentation. It's really interesting to hear what you folks are using down here for hydrotechnical design. I was just to follow up on the questions that Demetrius was asking. Does not WashDOT require you to look at some sort of a climate change approach to design flows for the future? I mean, if they're going to put in a bridge that's got a what 50 to 75-year design life, it's highly likely that the frequency curve, just to pick a static view of it, the frequency curve is going to change over that time. The historical conditions aren't likely to last. So I'm just curious if that's not the case, or if they're thinking about it, or what you might know about that.
No, they do. They do have a historical flow event that I can't think of it off the top of my head right now, but it takes into account. They do have it.
Okay, but they don't require you to use various methods for forecasting, or sorry, projecting into the future, or forecasting into the future, how, for example, the 100-year flow might change. If right now that's 100 CFS, perhaps in 50 or 75 years, that might actually be 150 CFS. That changes completely the dynamics that the bridge is encountering.
Correct. Yes. Yeah. But they do have a criteria in there. I'm not with the DOT anymore. And again, I just can't. I would have to look it up and let you know on it. But they do have one.
Okay. Thank you. I just wanted to kind of explore that. So thank you.
Mm-hmm.
Thank you very much for your question, Jeff. We crossed the top of the hour. I would like to thank you again, Rose, and thank you everybody for being on our presentation today. Next presentation is on February 17th, and I hope I'll see you all again on the next one. Okay, thank you very much. Have a nice evening.